Hello everyone. Today we are going to work on the section 15.2 that is double integrals over general regions. Okay. Now what happens is what we did in the previous video is double integrals over rectangular region. What is the difference between it and between both? For example, if we were to do the same problem in the previous section, it would have been integral 0 to 1, integral 0 to 1 sine y squared dy dx. This would have been a double integral over a rectangle. Okay, why do we say that? Because our domain is like your y is really changing from 0 to 1 and your x is also changing from 0 to 1, and the inside or the first variable of integration is y, so that corresponds to the first integration, and the second variable of integration is x, so that corresponds to the second integral. Okay, so your domain is really I'm just drawing the domain, not the whole thing. X is varying from 0 to 1, y is varying from 0 to 1, so you have this entire thing here. So your curve lies in sine y squared is somewhere over here. I mean, not over here. We are integrating this function over this entire region. So that was a double integral over a rectangle. But always we don't always get the rectangle. We could get any general region, meaning we could just get a circle, or we could get an ellipse, or we could get a any crooked shape like that. We could get any such shape. Domain could have been that, domain could have been this, the domain could have been a picture like that. It need not be rectangle. So that's why that's where this section comes into play. We are finding the double integral over a general region, region. So that means here the problem that we were given was 0 to 1, and I think 0 to 1 and x to 1, and you had sine y squared dy dx. Okay, sine y squared dy dx. Now this is general. Again, here the domain is over a rectangular region because the limits of integration here are numbers. Limits of integration are numbers in this case. But whereas here the limits of integration involve variables as well. I mean, you could have had. I mean, if the variables occur, they have to occur in the first integral, because the outside ones you want it to be numbers. Otherwise, you would not be able to integrate. But this is what it is. Now, what does that mean? It means that what is your domain? Your x values are changing from 0 to 1. So somewhere here 0 to 1. Your y values are changing from x to 1. So what that means, this is y equals x to y equals 1. The graph of y equals x would be that, and the graph of y equals 1 would be that. So that means you're really interested in integrating this over integrating sine of y squared over this region, and this is not rectangle. In this case, this is a triangle. I hope that is clear. So the moment you integrate over a general region, you could get the domain could be a circle, it could be an ellipse, it could be any different shape, or it could be a triangle. It need not be a rectangle. That's the main difference. That's the hiccup we are trying to overcome. This was section 15.1. Now we are taking one step forward and trying to find what is that, double integral over a general region in the section 15.2. I hope you understand the difference between those two now. Now let's start with the problem here. Okay, evaluate the iterated integral 0 to 1 and x to 1 sine y squared dy dx. And now you understood why we are really integrating over the region here. So that's what it is, and this is here. So this is y equals 1, and this is y equals x. So you are in this region. Okay, you are integrating sine y squared over this region. I mean, the sine y squared curve would be somewhere, I don't know how to graph it, but it is definitely oscillating curve. Okay, so now if I were to I mean, let's start with a problem. 0 to 1 and x to 1 and you have a sine of y squared dy dx. Okay, now the first thing I want you to understand is this is in the form of c to d integral g1 of x to the g2 of x. Okay, sine of y squared and this dy dx. Okay, so that means if I have to write it, c to d integral g1 of x to g2 of x f of xy or f of xy dy dx, and that's what your textbook actually refers to it as. I think yeah, the type 1 region. Okay, that's all. I also mentioned it in the lecture notes. That's what it refers to, the type 1 region. Type 1, it doesn't matter. I mean, they don't get carried away by these numbers as type 1 or type 2, but try to understand the concept behind it. It just means that the the limits of y are expressed as a functions of x, and the limits of x are expressed as numbers. That's what is happening here. The limits of y are expressed as functions. I mean, y equals x is a straight line with a slope of 45 degrees and it's rising up. Y equals 1 is a constant function, so it's a horizontal line, and you are really interested in that reason. Okay, so this is like, according to our textbook, it is a type 1 problem. Okay, and now let's go ahead and integrate. What is the integral of sine y squared? I mean, what are the techniques of integration that we are going to treat? I mean, first we are going to integrate with respect to y, right? So you're going to treat that the second integral doesn't exist for now, and we're going to work on this one. Okay, now, so what are the techniques of integration that you know? Do you know any formula for integrating sine y squared? No. You know the formula for integral of sine y, that is negative cosine y, but sine y squared you don't know anything. Can you use u substitution on this? Go ahead and try, but let me just make it short and sweet by saying it will not work out. Okay, then move to calc 2. I mean, can you use integration by parts? Answer is no, but you're welcome to try. Trig integrals? No. Trig substitution? No. Then partial fractions? No. Is it an improper integral? No. So all these things doesn't work out. So can you use polar coordinates that you learned in calc 1, calc 2? No, not yet. So all the things that you learned, the techniques of integration that you learned in calc 1 and calc 2 are out of the window, right? So that means this problem, don't rush into saying that this problem is unsolvable. Okay, so let's see. This is our domain. So can we change the limits of integration? Because in the integrated integral, you can change the limits of integration by using Fubini's theorem. So I want to be able to write integral of sine, okay, y squared dx dy. Does it help? I'm trying. I mean, because it did not work out, I'm trying changing the limits of integration. But when I want to integrate with respect to x, what am I seeing? My limits of integration for y would be 0 to 1, okay? And my limits of integration for x would be what? X equals 0 to y. You see that? Why? Because y equals x means x equals y. So that's what I'm trying to look at, because then it would make the same thing. So, but would that help? So first I'm going to evaluate this integral. When I evaluate this integral, I'm going to integrate with respect to x. So I'm going to treat all the terms involving y as a constant. So integral 0 to 1, you get sine y squared. Integral 0 to y dx, and you get like that's going to be in dy. So now when you integrate this, you get 0 to 1 sine y squared. Integral of 1 is x itself, and upon substituting the limits of integration, the limits of integration is from 0 to y. Upon substituting the limits of integration, you get y minus 0, and you get sine y squared dy. So that's going to be integral 0 to 1 y sine y squared dy. Okay. So you see, if I went y first and x next, nothing worked out. So I changed the limits of integration. I changed the order of integration because Fubini's theorem says that you can shift it. But because I changed the order of integration, my limits of integration also changed. Okay, but because of which I am at this place. Now I have only single integral, you see that, so that means all my knowledge of Calc 1 and Calc 2, I can use it now, okay, they are not waste of time. So first thing is there any formula for it? No. Can I use substitution? Yes. So I'm gonna say my y squared is gonna be u, so I'm gonna say 2y is gonna be du dy, right? So I'm gonna isolate dy from here. When I isolate dy, I get du divided by 2y. So I'm gonna pretend as if I don't have limits of integration. So I get y times sine u. dy is du divided by 2y. I mean, if you learned it in a different way, it's okay. Now y gets cancelled out. 1/2 is a constant, so that steps out. So you get integral of sine u. What is that? Sine u du. So that's gonna get you what? Upon integrating it, you get negative 1/2. Integral of sine u is cosine u, so you get cosine u. Now, upon back substituting, u is y squared here, so you get negative 1/2 of cosine of y squared. And now you substitute the limits of integration, and the limits of integration is 0 to 1. So that gives you negative 1/2 cosine 1 squared minus again negative 1/2 cosine of 0, right? So that's going to give you negative 1/2 cosine of 1 plus 1/2 cosine 0 is 1 here, so that's what you get. So you get 1/2 minus 1/2 cosine of 1, right? So this is what you get. This is what you get actually. So the integration is that. So this is type 1. Now if you see this integral, I want to bring your attention back to this. The answer is 1/2 minus 1/2 cosine 1. I hope it's the right answer. If it's not, if I made any mistakes, please fix it. Now the next thing is I want to bring your attention to this. This is in the form of integral. I mean, you know, c to d, but this is not a function of x anymore, but this is a function of y. So I mean, you know, you can write this as maybe I don't know what your textbook uses. Do they use a different variable h, or do they use the same function g? I don't know. Let me be consistent. So this is h1 of y, so it's a function of y, to h2 of y, then you get f of x y dy. Okay, this is a type 2 integral. I mean, you know, this is of the kind type 2, and that's what exactly it's saying. If f is a continuous on type 1, okay, type 2 region, let's call it, because the previous one was type 1, okay, type 2 region D, such that you see the limits of y are numbers, the limits of x are the functions of y, then you can write it like that. So that's what we just did here in this example. Okay, I hope this is clear. So to summarize, first what we did was we explained the difference between the section 15.1 and 15.2. In 15.1, the double integral was over a rectangle. How did we know that? Because the limits of integration were numbers. So that's what we did. But what if our domain was not just a rectangle? What if it was a circle? Or what if it was an ellipse? What if it was a general region? Or what if it was a triangle? So we wanted to integrate, we want to evaluate double integrals over a general region. I mean, you know, when you find double integral, you are finding the volume, right? So you're finding a general region. I mean, you know, so for that, there were two types of integration. One is, they call it type 1 and type 2, it doesn't matter. In one type, I mean, the limits of y are expressed as functions of x. In another type, the limits of y are expressed, the limits of x are expressed as the functions of y. Okay. Okay, this is dx dy here. Okay, and then in this example, when we tried to evaluate in this order of integration, it did not work out. We did not get any path forward. So what we did was, because it's continuous, sine y squared is continuous over the domain, we used Fubini's theorem and we changed the order of integration. Because we are changing the order of integration, we change the limits of integration. Okay, upon changing the limits of integration, we got a suitable answer. I hope this is clear to you all. I'm going to upload the rest of the problems as well on Falcon Online. For those of you who attended the session on Friday, thank you so much. It was nice seeing you and your pets. And for those of you who were not able to make it to the meeting on Friday, I mean, it's okay. It's okay. I hope you're safe and healthy. So I hope your family is also safe and healthy. Stay safe and healthy. I will see you again on Friday at about 10:30 a.m. on web meeting. Okay. Till then, bye bye and have a nice week ahead. Take care. Bye bye.